So we're going to start talking about ions and how to draw the Lewis dot structure for an ion and for an ionic compound. So first, when we're going to draw the Lewis dot structure for an ion, we need to think about how many valence electrons the neutral atom has, whether it's going to gain or lose electrons in order to attain its greatest stability, and then what the charge is going to be after that. So let's talk about stability for a second. Elements are the most stable whenever they have a full shell of valence electrons, whenever they have 8 valence electrons on the outside of the atom. This is why the noble gases are stable and do not react with other elements. They already have a full valence shell of 8 electrons, and so they don't need to gain or lose or bond with anything. They have the perfect number of valence electrons. Other elements want that same thing. They want 8 valence electrons, but many of them are going to have to gain or lose electrons in order to do that. So in the first example, we have sodium. Sodium is a metal. It's an alkali metal in group 1 of the periodic table. What that means is that sodium has 1 valence electron on the outside of the atom. 1 valence electron is not stable at all. In order to be stable, it needs a full shell of 8 valence electrons. The problem is that metals on this side of the periodic table do not have a high electronegativity. They're not able to grab electrons from other places and add them to their valence shell. Instead, what sodium is going to do, because it's not electronegative, is it's going to lose that 1 valence electron it has and drop back to the same electron configuration as neon, a noble gas with 8 valence electrons. So by losing that 1 electron on the third energy level, it makes the second energy level its valence shell, which is naturally full. So let's think about how we would represent that using Lewis dot structures. So for sodium, since it's in group 1, the neutral atom has 1 valence electron, which I represent with 1 dot. It's going to lose that 1 valence electron and get a charge of positive 1. Because when elements lose electrons, they lose negative energy. And since now it has 1 more proton than electron, it's going to have a positive valence charge. For the ion, we're going to represent that by simply taking off that electron from its original Lewis dot structure. So I'm going to draw the ion with no dot. I'm going to put brackets around it and put that valence charge on the outside. So let's try another one. We can do this with chlorine. Chlorine on the periodic table is a halogen. It's in group 7A, meaning it naturally has 7 valence electrons. And I would draw the Lewis dot structure with 7 dots. In order to be stable, it needs a full valence shell of 8 electrons. The nonmetals on this side of the periodic table have a much higher electronegativity, and they are able to attract electrons to themselves. So nonmetals tend to gain electrons in order to fill their valence shell, meaning it needs to get to 8 valence electrons by gaining 1. If it gains an electron, it's gaining negative energy and now has 1 more electron than proton, so its valence charge is going to be negative 1. And to draw the Lewis dot structure of the ion, I would put the symbol, I would put the original valence electrons, I would add the 1 to make a full valence shell, put brackets around it, and put that charge on the outside. So remember, metals tend to lose electrons in order to attain a full valence shell. They do not have much electronegativity, and so it's easier for them just to lose their electrons. Nonmetals have a strong electronegativity and are able to gain electrons in order to fill their valence shell. This concept is also seen whenever we draw the Lewis dot structure for a compound. If I look at the compound formula, I can see a metal and a nonmetal. I need to think about calcium for a second. Calcium is in group 2A, meaning it has 2 valence electrons. Also meaning it has a very low electronegativity because it's a metal on this side of the periodic table. Since calcium has 2 valence electrons, calcium is going to lose those 2 electrons and lose that 4th energy level and drop back to argon's electron configuration with a full valence shell. So the ion for calcium would not have the 2 dots that it originally would. It would have the brackets on the outside, and it would have that +2 charge. Oxygen, again, is a nonmetal. So it's over here in group 6A. It needs to have a full valence shell of 8 electrons. And because oxygen has a high electronegativity as a nonmetal, it's going to gain those 2 electrons. So I start off with the original 6. I add the 2 that are gained, and then I put brackets around it and put that charge on the outside. Another way to think about this, whenever we draw the ionic compound, is that the 2 electrons that calcium lost were gained by oxygen. By doing this, each element was able to attain a full valence shell on its outside and get greater stability. To draw the ionic compound Lewis dot structure, we just draw those 2 particles together. Be careful for some of the ones that have multiple ions in them. Don't put the 2 positives next to each other. Don't put the 2 negatives next to each other. In nature, things want to have a separation of charge. We want the positives and negatives to alternate in order to maximize their attraction. So when you draw something like this magnesium chloride here, again, always think about how many valence electrons it has. Magnesium is another alkaline earth metal with 2 valence electrons. And then think about how it's going to attain that full shell. Is it going to gain 6 more? Probably not. Again, because it's a metal. Metals lack electronegativity and tend to lose their electrons in order to get their full valence shell. So magnesium is going to lose those 2 electrons to drop back to neon's electron configuration, which has a full stable shell of 8. And when it does that, we show it with no dots and that +2 charge for the 2 electrons that were lost. So notice that metals are going to tend to look like this. They're not going to have any dots as ions. They lose those dots in order to get their full valence shell and gain stability. And then however many electrons are lost are represented as a positive charge. If we think about chlorine, we already drew chlorine on the other side. Chlorine was that halogen with 7 valence electrons and gains 1 more to get the same electron configuration as argon. So I draw the original 7 valence electrons, I add the 1 extra, and I put that charge on the outside. And again, you'll notice that nonmetals tend to have a full valence shell, showing us all 8 electrons, including the ones that were gained, brackets on the outside, and the charge. Now, if I look at this formula, I see a little subscript. That little number tells me that there are actually 2 chlorines in this compound, which means that I need to draw the chloride ion twice whenever I represent the compound. I'm not going to put those 2 chlorines next to each other. Again, we want to maximize attraction by alternating positive and negative charge. We want to make sure that the negatives are as far apart from each other as possible, and that the positives are as far apart from each other as possible, and that positives and negatives are in as much contact as possible. That maximizes attraction. So I'm going to draw 1 chlorine on one side. I just have to think about how to position it. I'm going to draw 1 chlorine on one side. Then I'm going to put the magnesium in the middle. And then I'm going to put the other chlorine on the other side. So again, I've separated the 2 negative particles. I've alternated negative and positive to maximize attraction. And this would be the correct Lewis dot structure for this ionic compound.